Hello and welcome everybody. Today I want to show you how to implement the Fibonacci sequence in code. This is not really Python specific, but it's a good example to get started with Python. The point I want to make today is that there are two different ways to implement the Fibonacci sequence. The first one is basically a one-to-one translation of the mathematical definition, whereas the second is a little bit fancier because it's using a loop instead of recursion, and it also has very different performance characteristics. So today we're going to implement both versions, and in the end we will also measure the performance of the two versions so that we have a foundation to compare them to each other. So let's get started with the first version, namely the easier to understand version that's using recursion. So this will be our function signature. It's basically mapping one integer to another integer, where n is the index of the Fibonacci number in the sequence that we actually want to compute. As you saw before, the Fibonacci sequence in mathematics is simply defined as the sum of its two predecessors. We can easily write this with recursion in Python. Let's do this quickly. As you can see, this would be an infinite loop at the moment because there's no exit condition for our recursion, so we have to add this. And the first two elements, or rather the Fibonacci numbers with index 0 and 1, are hard-coded to equal to 1 because that's the entry point into the mathematical sequence, and we can easily express this in Python code. So if n equals 0 or n equals 1, then we return 1, and otherwise we return the sum of the two predecessors. Last but not least, to ensure that this really works as expected, we can add a couple of assertions. Let's do this also. And so on. You get the idea. Now I can run this program. Let's see. And it doesn't print anything. That means the assertions were all fulfilled. Let me break it for a second so that we can see the assertion error to make sure this is actually doing what we think it is. So let's break this assertion, for instance. Now if I run it again, then I get an assertion error, as you can see. So that's already the first implementation, and now we can do the second implementation that will be using loops instead. Copy this real quick. Let's update the documentation using a loop. Return 1. Okay. So this will be our second function. I can copy the assertions and replace this. Now we already have a test or a failing test that will guide us as we continue with our implementation. So for the loop version, we basically need two variables. Let's call them A and B and set them both to 1, and then we will return one of these. We need a loop, of course. We will loop over the range that goes from 2 up to n plus 1. And in here we will basically calculate the next Fibonacci number from the two predecessors that are the variables A and B. And then we will assign our newly calculated Fibonacci number to the variable B, and the prior value of B we assign to A. So basically we shift everything one place to the left, so to say. And now last but not least, we have to do our performance analysis, and for that I'm gonna create something that resembles a table with columns for the measure time of the recursive approach as well as the measure time for the loop-based approach. So this already looks okay for a table header, and we can, let's say, do 11 samples for Fibonacci numbers 0, 4, 8 and so on up to 40. That makes 11 samples. That means in total we will calculate 22 Fibonacci numbers and list them in our table. To actually measure the runtime of each function invocation, we can use the built-in time module. And the time module has a function called perf counter, and this gives us the total CPU time that the program has consumed so far. And if we call perf time 2 times, one time before we invoke our Fibonacci function and one time after, we can calculate the difference, and from the difference we get the duration. And if we then run this, we will get a really nice table. And as you can see, this is a pretty amazing result because it clearly shows how different the two algorithms are. As you can see in the loop version, you can hardly see that it is taking any time at all, whereas the recursive approach is really quite slow. And the reason for the huge difference is the complexity of the two algorithms, because the loop-based approach has linear complexity, whereas the recursive approach has exponential complexity. That's it for today. That's what I wanted to talk about. Thank you very much for watching, and hopefully see you soon. Bye bye.